All right, week 111. What is up, everyone? Welcome to week 111 of building my own operating system. Thanks for joining. Give me a moment as usual to set up. Got the Discord ping sent out. All good. Cat Flare. Nice to see you, Cat Flare. Punctual as always. All right. Whew. Well, I'm glad to be back. I've been waiting for this all week. And I'm really excited to think about more scheduler related things today. Test passed. Whew. Okay. I'm so relieved. What's up? What's up? Sorry, Vex. Nice to see you. Just in case, we'll run it again with the test one. All right, cool. Well, what's up? What's up, delicious noodles? That's such a sick username. All right. Well, cool. I'm super excited, guys. I've been waiting all week. I've been thinking about a bunch of stuff that I want to do today. And I'm excited to finally have a bit of a chance. So get the break timer primed and going already. Man, I want to eat noodles right now. Straight up. Straight up. What's up, A-Sans? What is up, man? What is up? Doing all right. Had kind of a rough week, to be honest, but it's always a good week when I can stream. So what's up with you? How you doing? We got a bunch of hungry people in the chat today. Some noodle activities. Cat Flare going back to school. Sorry to hear that. That sucks. Just kidding. School is great. It's great to learn things. But yeah, school can be a drag. Hope you get through your schooling and make it into a job at some point or whatever you want to do. Tell us about the internship, though. Anything interesting in the internship? Was it aligned with any of your interests? Or man, my electrotechnics teacher's ass. Damn, that sucks. All right, last time we spent the entire stream philosophizing about a kind of useless topic, which is making the scheduler, like the yield routines, preemptible. And the outcome was that is a bad idea. So I'm just going to make a little to-do list for what we're going to get into today. Well, maybe we sort of already have this. But let me just start from scratch. And so a couple of things on my mind. Make yield stub interrupt safe by disabling interrupts. Yeah. That's something we could do. Another idea is to implement an API that allows an interrupt to yield the scheduler needed for preemptive multitasking. That is a separate task. But people be chatting it up in the chat. Hey, Sans, I started using Miro for a personal project. It's actually useful to land ideas, like declutter your mind. Absolutely. Can you imagine if this was all in my mind? My mind would literally explode. And it's sort of nice in contrast to like a like text document or notes or traditional notes, in that you can be very visual with it. It can also support quite a lot of data, images. You can be very visual with things. Yeah. VA80, what's good? Made it to a stream. Listen, let's go. Glad to have you here. Thanks for chatting it up so much in the Discord last week. Creating some activity in there. It can be a little bit quiet sometimes. Sorry, Vex. Why are you making an OS? Just for fun. Yeah, for fun, for learning. Because I want to. I'm inspired. I want to learn about this stuff. That's all reasons why. Okay. All right. Another topic. Rethink the per CPU data area. Or not. For later. Yeah. Excuse me. That's a GS thing. Couple ideas for today. What did we have drafted up last time? Adding more than 2 kernel tasks. Adding a kernel thread exit. That sounds nice. Adding an idle thread. All right. This is not really actionable, but building mutex using these primitives. So just disable interrupts. Let's just next time implement the CLI STI solution for disabling preemption during yield. Word. Okay. Catflare asks, do I have any other projects other than this? No. This is my one and only side project. Yeah, it's pretty much all I have time for, unfortunately. So and even a couple hours a week is sort of maxes me out. So this is my one and only focus as far as projects. Okay, let's I think we have enough to get started. So my goal, yeah, gonna think about the interrupt safety thing. Going to think about setting ourselves up for preemptive multitasking, maybe the kernel thread exit. So at a high level, I feel like I should have some kind of high level roadmap. Let me update the high level roadmap. Let's update the high level roadmap. So this got deferred. It's not actually that important. It's totally fine to run on bootloader page tables for the near term. So it's got deferred. Paging virtual memory. Let's call it basic paging, being able to map pages, which I will distinguish from paging on map pages. Requires thinking about how and where to store a ref count. We're going to defer that for later, not so important. So this is done. We have some very basic paging infrastructure. I'm going to not do unmap for a while. Level topic, cooperative multitasking. So at a very high level, we're doing cooperative multitasking first, then we're going to do preemptive multitasking. We're not there yet. And the idea here is kernel basic building blocks for scheduling, kernel threads, yielding will allow us to implement texts in the future. Okay, so we're still over here, and let's take a look at what we have so far. So basic kernel tasks, basic context switch out in, basic scheduler, round robin, we have all this. Basic task storage using ETL container, got that. So we got a bunch of stuff working. Just drag the progress bar over. But what's on the edge is interrupt safety. So over here in the future, we're going to have things like setting up our timer, interrupt. So yeah, just bear with me while I do a bit of project planning for what we're kind of doing. So timer interrupt. And that's really where the preemptive multitasking hits the road. And I think after that point, we might get into drivers, IO, something like that. Could be cool. These are all, got the kernel class, that's done. Serial driver would be over here. Some other future ideas. Okay, so this is a high-level roadmap, kind of what we're working with. Scheduler APIs for yield, exit, interrupt, yield. VA80, will you let us use this OS down the road? That is, we'll see. Yeah, I think I do plan to release it at some point. I'm still thinking about how I want to do that. For the moment, I'm really enjoying having it just be my nice little private personal project. But I'm not ruling it out, letting other people use it in the future. Yo, off and on. Nice to see you, man. Thank you very much. It's been a while. Thank you very much. Appreciate that. Yeah, nice to see you. Hope you're doing well with all that stuff you got going on. You said you dropped out of school, you're working on your company, startup, pursuing your own path. I wish you all the best in that area, man. Yeah, I know you know what's best for yourself, and it's important to recognize when your current situation is not working for you, when it's not leading you where you want to go. So good for you for making your own calls. All right, let's jump into it. So starting task number 1, make the yield stub interrupt safe. So let's talk about that. What do I mean? What do I mean by making the yield stub interrupt safe? So as usual, let's just build. Okay. We are building okay. So really it's not that deep. So here's the problem. Let's imagine a future world where we have preemptive multitasking. We don't have that. Let's imagine a future world where this task 1 is running and it calls yield to schedule itself out for any reason. Maybe it's blocked out of mutex. So let's walk through the path. Call yield, which immediately jumps to this assembly stub. It's implemented right here. We start executing instructions in our stub. And then what happens if we get a timer interrupt for preemption? Task 1 is in the middle. Task 1 even sort of has exited a little bit. It's technically task 1 is in this twilight zone transition point where it is actively in the middle of scheduling itself out. But it's in the middle of this kind of sensitive operation. And then an interrupt comes in and wants to schedule something else. Last week we decided that maybe there is a technically possible way to support this. But in general, that's just simply not worth the complexity of allowing that is not worth it. And so therefore, disable interrupts. No preemption allowed during scheduler yield. Let's think about that. Right. So here's the part where we can think, all right, excuse me for 1 second. Gotta get a tissue. All right. So let's get out. So let's think about this. Also just curious, Do I have other instances? No, there's no other instances of clearing interrupts in the OS. So basically, yeah, we need to disable interrupts with the CLI instruction. Maybe we'll also just get the JOS2 out, because I know JOS2 does this. Let's just... It's not that hard. Disable CLI and ST are the instructions we need. So we can call CLI here. I think realistically, it would be nice to do, like, it's interesting to think about how we would do this in an architecture independent way, but this is literally assembly code, and so that's kind of stupid. So I think it's fine to just hard code the instruction in here. This is literally assembly. So we have the CLI, and let's think a little bit through the concurrency of this situation. I'm just gonna take a screenshot just to help illustrate that. So what I'm talking about is right here. Let's think about the concurrency. So in general, with our task, this is sort of like application layer, even though it's still in the kernel to kernel thread, it's conceptually still application layer code. And so this is totally preemptible. That's the design. And any of this code, anything running here, preemption is totally fair game. Then here's where it gets interesting. At what point do we stop allowing preemption? And I've decided that as soon as we call into the scheduler, we disable preemption. Currently we're disabling interrupts. Interrupts and preemption are not technically the same thing, but some global state, something like that. All right, we got our first 20-minute break. Feel free to join me in a nice little 20-second break. Feel free. Nice. VA80 doing some push-ups in the 20-minute, 20-second break. Dude's gonna get ripped during the OS dev stream, that's for sure. What's up, Aditya? What scheduling scheme are you going to implement? I have a basic round robin right now, and I'm not so interested in different scheduling algorithms. I'm more interested in preemption. What level of preemption we can get, and so I'm not planning to change the round robin for short term. Okay, so let's think this through. And so we're gonna call into the yield. Theoretically, we could even disable interrupts straight up right here, but I like the idea of having this be a single jump instruction. This is supposed to be a really thin stub. So I like the idea of having this being a single jump instruction. I think that should be safe. We get here. And we can think about really what's the difference here. So if the CLI, I think it's fine. I think the important part is that the body of this runs without getting interrupted. I think that's the most important part. So just, I think having the CLI is right here. And so, okay, so disabling interrupts. Good. And so now, I even wonder, you know, I've always wondered how best to visualize these things. Let's make a timeline. Let's add some events. Maybe we'll add some different, I don't even know. I know there's some different ways to visualize these things, but we got task 1. Say we're okay. So exec task 1, a yield happens. You know what? Let's even say let's exec task 1. Timer interrupt. It's executing task 1, just like normal. Timer interrupt happens, let's just say in a totally normal situation. Timer interrupt happens. Runs scheduler.insert yield from interrupt or something like this. Stops. Execution flow goes into the timer interrupt. Let's say we got task 2. This thing is stopped. This thing hits the scheduler. Sequence of events, task 2 resumes. Runs for a while. Same deal happens. And we go back up here. Oh my gosh, did I just get a donation? Mohit. Oh my goodness. My first ever donation on the stream. What just happened? Thank you so much. I have never received a donation on stream before. I didn't even know how it was possible. Wow. I need to screenshot this. Holy crap. That's going right over here. Thank you so much. I really appreciate that. I've never gotten a donation before. I didn't even know. I barely even knew that was even possible on my account. So that's crazy. I've never asked for them. It's just never been something I've really done. So I want to really give a thank you to Mohit. I can't see the full username, but I just want to say deeply, deeply appreciate that. Thank you so much. Very cool. That's pinned up in the chat. That's pinned up in the Miro permanently. That's staying right here. We're going for the timer interrupt straight into the YouTube chat. All right. So let's thank you. And so now, this is basically the normal flow of how things work. One thing running, hit the timer interrupt, select something else. That okay, strictly speaking, let's be very particular about the order of things here. So it's technically, these things happen in the same instant. So it needs to be very clear it's a vertical line. The stop happens and the timer interrupt fires. And now we're back executing task 1. And then here's the part I want to explore. And so I think that deserves to have the scheduler yield from interrupt renamed. Yeah, we yeah, these names are all totally up for renaming. I haven't really thought about good names. Also, nice to see you, James. Thanks for coming back. So again, we're back in task 1. And now task 1 is going to do a dot yield. Oh my gosh. I am God's eye with the donation. This is crazy. Y'all are doing too much right now. Thank you so much. This is wild. Get that pinned. You get a spot. Yeah, I guess that's the rule now. If you make a donation, you're getting posted up in my board. That's what's going on. Oh my, VA80. Yo, this is nuts. This is nuts, y'all. Thank you so much. I'm blushing right now. Yeah, people trying to get methods named after themselves. Yeah, that's how it's gonna work. That's how I'm gonna make a living. I'm gonna make a living by putting add placements in my function names. So yeah, like if you pay a sufficient amount of money, I will put your name into my function names or class names. That's freaking hilarious. You are forever part. You're getting put into the symbols of my binary. That's what I'm doing to you if you donate to my streams. It's crazy. What's the threshold? Oh my gosh, I don't even know. I mean, I got to figure out the pricing on that. I need to be conscious of the economics around that decision. Otherwise, the OS code is going to be splattered with people's names and every variable, every function name, every class name. It's just going to be people's names everywhere. I can't have that. So I need to think more about that. But this is wild. I'm going to give y'all a big star. Thank you. Don't know how to use this tool. Thank you very much. Okay. That's well. I appreciate y'all. Thank you. So, dot yield. So here's the critical point. Task 1. Also, I think there was a question. Aditya, shouldn't task 1 stop, follow the timer interrupt? So task 1. So I think this is approximately what I want to say. Task 1 stops, this thing runs, resumes task 2, it stops again on the interrupt, and then we come back to task 1. And then, unlike before, task 1 hits the yield. And so what we've done is we've disabled interrupts. And so now we're in the critical yield. I'm going to color this a little bit different to mark that we are in a critical zone. Make it pink or something like that. The yield path is going to run. And here's what is going to happen. So here's how the yield path looks. We have this thing, and it saves a bunch of state calls into here, which is over here. The yield path finds the current task, copies the scratch area into the register state, and then hits yield impl, which does this. We may update the state of the current task to be not runnable. We choose a next task. We switch into it. Switch to task. Looks like this. So this is the sequence of I chose these kind of obnoxiously long names, but a couple of things here. This is the yield path. Basically, the main point is that during all of these critical scheduler operations, like all of this code does not participate in the normal flow of the application layer kernel code, so to speak, which is this. This is all special code. It is not normally preemptible code. It exists at sort of the system layer in order to provide threads, and so therefore nothing of this is preemptible. In the simplest version of our kernel design, we just simply ensure that all of these things run back to back to back, and if an interrupt comes in, if an interrupt comes, well, it's blocked. We're not allowing that to happen. And so this is sort of what we want here. We do not want some weird thing happening where this thing like we're in the middle of this, then we come back into here, and then like this thing starts running again. Like, to illustrate it visually, this is bad. This is not supported, right? This is bad. This is what we're doing. So if a timer interrupt comes in, we block it. Oh man, James with the dono, crazy. We got the wall of donations today. I appreciate y'all. This is crazy. If you find a delete method that needs renaming, here's my hat in the ring list buffer. Let me show some love to this. Gonna hit the heart. Hit the heart. I appreciate it, guys. This is crazy. The fact. What's up, Ashbourne? What's up, Danny? Nice to see everyone. Yo, thanks. All right. So, resize this just a little bit. So, right. So the point is, this sequence needs to run uninterrupted. The way we do this is via this, the CLI. That's how we ensure the CLI runs, and that ensures that, change the color just to differentiate that. That ensures, actually no, it's too confusing to have an arrow here. The CLI ensures that timer runs get blocked. This thing runs to completion, but then the question is, when do we re-enable interrupts? And basically the answer to that question is, as soon as, or basically just to complete the diagram, switch to task jumps over here. That's sort of, maybe it's helpful to make these not be diagonal lines. I feel like the diagonal lines are a little bit misleading. So these changes are abrupt. Yeah. So this is sort of what happens here. When a yield happens, we switch to task 2. Let's make this a straight line. Right. And so we need to enable interrupts when switching back to another task. Because we want, as soon as task 2's application layer code runs again, we want that to participate in scheduling. So where is that going to be? Let's take a look. So we're talking, it's basically, the point is it happens at the very end of the process, which is this function called switch to task, which takes a task index. VA80, time to go to bed. Good night. Good night. Yeah, thanks for joining VA80. It's really nice to see you. Thanks again for the contribution to the channel and for hanging out and the good vibes. Have a nice one. I'll catch you later. So we find the task, we set its state to running, and then we do the sequence of assembly instructions that restores the register state and jumps back into the task. And so really, the final moment to re-enable interrupts is basically right here. It's right here. And so I think I need to point out that we're doing this preparation work. I don't actually have any of this timer interrupt stuff yet. I don't have preemptive multitasking yet, but I want to set myself up to be in a good position for when I do have it. So that's sort of the flow. Let's make a line here. Say this sequence needs to execute uninterrupted. Okay, just to finish the diagram, task 1 resumes, and then our typical flow will happen. Stops. Right, this is an illustration of how we want this to work. And we come back into task 1. Sort of the idea. Okay. So basically that's the idea. Re-enable interrupts. So I've added 2 lines of code to the OS. These 2 kind of critical lines. I'm gonna drop this. Literally 2 assembly instructions. Now the question is, how do we test this? How do we test this? And the thing is, I'm not sure. I don't have, since I don't have a timer interrupt, I am not even sure I can test this code. I don't really have interrupt handling, but we've reached the second 20-second break, so feel free to join me for a little break. What's up, Checkwob? You might be able to fire an NMI from the Kimu console. Let's ask the AI. First of all, I'm gonna ask the AI for some code review. I'm gonna pin this context. I'm also pin this context. Okay. Let's see if we get the hyper whisper out. Oh man, I've reached my 5-minute. I need to pay for that thing. That's kind of annoying. Okay, I just want to talk to the AI. The whisper flow. Okay, I'm just gonna type it out. So please code review these 2 lines. I've added a CLI STI to my yield sequence to disable preemption during these critical operations. First of all, does this sound to you? Also, how might I test this if I don't currently have a timer interrupt? I was thinking of manually triggering an exception from within the yield stub, e.g. software int or so, and observing that that handler does not run until interrupts are enabled, but I don't think this will work because that's an exception and not an interrupt. Let me just fire this off at the Opus 4.6. We'll see what it says. So checklog maybe is suggesting maybe firing an NMI from the human console. James is saying, could you have a string of characters indicating which task or interrupt is currently executing and then test the results against expected? I think I need to understand that idea better. It's currently executing. Do you mean like some like output, like output to the console? Yeah, I mean, yeah, it's some kind of prints could do it. Just the problem is, how do we? I want to test that interrupts are disabled. And I just don't know how to actually. Ideally, we would try to make sure an interrupt happened in the critical sequence, and we would observe that the handler just does not run for a while. So let's check this. So what does it say? First of all, is the approach sound? Yes. Disabling interrupts around the save restore is a textbook approach. Bug is I'm missing something, whatever. STI has a one instruction interrupt shadow. Oh, that's kind of interesting. I did not know that. That's some pretty specifically elite knowledge, in my opinion. STI ret is atomic with respect to interrupts. So that's perfect, actually, because, yeah. Oh, the start path. Oh, that's interesting. So that's maybe a bug. Testing without timer interrupt. Correct int CLI. Practical approaches. GDB. We can just GDB things. We can assert. That's yes, that's actually probably good. I like that idea. Set up a fast firing timer then yield. Okay, so it actually didn't even suggest a solution. James is saying, so for example, when the timer interrupt fires, XCBuff would have 1 T2 after task 2 is started after the timer interrupt returns from yield. Would have 1 after task 2 started after time. Yeah, okay, gotcha. Yeah. So you're just saying we have some kind of console output that is representing the current state of what's happening, whether task 1 is happening, whether the timer interrupt is happening, or task 2 is running. And that sounds plausible. That sounds like a good idea. Only problem is I just don't have a timer interrupt right now. I haven't set that up, and maybe it's not that hard. Maybe we could do it very quickly right now, but in general, I was hoping to defer the idea of getting into preemptive multitasking until we're like really ready to properly do that. And I don't quite think we're there yet, but that's a good idea. Yeah, that's a good idea. So I think we cannot actually test this. Yo, NSG, what is up? Nice to see you. Thanks for popping in. Yeah, NSG, nice to have you here. We are working on making sure my scheduler sequence is interrupt safe and preemption is disabled during specifically the yield operation right now for our cooperative multitasking, because that was sort of a point of weakness, a point of bugginess previously. I don't have preemption yet, but so we've just been kind of thinking about that. I'm curious, NSG, does your OS do something similar at all? Like when something in the OS, like when a kernel thread waits on a mutex, does it disable interrupts as a pretty early thing that it does? That's sort of what I'm thinking here. So, Asans, what language or tech stack do you use on a daily basis in your job? Do you use same VS Code theme and all? Kind of, actually. I have kind of replicated a very similar setup to what I do professionally in my home setup. I'm also using modern C++ in my job. I am using VS Code. I'm using a lot of these extensions. So yeah, it's not totally the same, but I've been trying to replicate a lot of the same setup. It just marks the thread as waiting on object. And when the mutex is freed, it gets scheduled. Right, but do you disable interrupts? Because otherwise you can get, like if I understood it correctly, you can, like this register save sequence can get interrupted, which is by a timer interrupt, which is not really good. So we're specifically talking about, yeah, this finer point of disabling interrupts in this sequence. And as we just discussed, I don't think I can test this. So at least right now, we'll need to make it a to-do. Have timer interrupts. Try stress testing the interrupt safety of the cooperative yield. Okay. So that was not a lot of code, but that was pretty much this. And as she says, well, when the timer interrupt occurs, or any interrupt, the interrupts are disabled, so nothing can interrupt it. Right, and so what we're talking about, though, is cooperative multitasking, where yield runs, and then a timer interrupt happens while in the middle of this. For example, if in the real-world application of this is kernel mutexes, where a thread might intentionally put itself to sleep, which is ultimately going to call scheduler.yield. And so that's the situation I'm asking about, where in your OS, when a kernel thread waits on a mutex within the kernel, I would kind of expect that it would need to disable interrupts to protect that critical section. It's not a matter of nested interrupts. It's a matter of preventing that initial interrupt from interrupting this cooperative critical section. guess now you look and sound like you're the most chill, dude. Yeah, the play got fired. You're like, okay, let's see. I appreciate that. Thank you. Yeah, try my best. Try my best. Luckily, I don't have such a high pressure job. I don't work on like a web service or something that can go down. I work on a hardware product, and we have a good testing and stuff. And so far I haven't shipped anything that bricked the fleet of devices or anything. So nothing too, yeah. I think my job has a chillness that matches me, perhaps. Okay. So now I'm kind of interested in this second task. Implement an API to allow an interrupt/exception to yield to the scheduler needed for preemptive multitasking. And so that goes back to what we were talking about last week, where imagine if task A is running and then it gets interrupted. And then she says, in my case, the yield function triggers a timer interrupt, and that handles the context preserve. Right, okay, your yield function triggers a timer interrupt, but the critical question is, does it disable interrupts? It needs to run this code, but this code needs to run with mutual exclusion. And ordinarily, if this code normally is invoked by the timer interrupt, it doesn't need to have a CLI here because, as you said, interrupts are already disabled. But in this case, it's running not in response to an interrupt. It's running in response to a cooperative call. And so that's just the detail here. And so, yeah. Okay, coming back to this thing, interrupt a special API. So in this case, when task A is running, then the interrupt handler fires. It is not using the normal cooperative yield API, because the cooperative yield API freezes basically the current state of whatever code is executing such that it can be resumed at a later point. But the thing is, with the timer interrupt, its goal is not to freeze its own state of the timer interrupt. Its goal is to freeze the state of the task that was running before the timer interrupt happened. And so that is going to require a little bit of a special routine. Yeah, since an interrupt got triggered, the ints are then disabled. I think we're slightly talking past each other. Like, in this situation, and really, in this situation, so as you said, an interrupt got triggered. In this situation, where we're talking about, a kernel task is running, and for some reason it hits yield. It does a cooperative yield into the scheduler. A reason why it might do this is a real life reason is if it's waiting on a mutex. There's no timer interrupt. There's no interrupt at all involved in this. It is just simply executing code that is going to call into the scheduler. No timer interrupt has fired. No interrupts have been disabled by the CPU automatically. It's going to cause us to enter the yield routine, which is going to save the state. And it's important to protect this critical section. Again, no interrupt has automatically fired to like cause this. This just code runs, and then the problem is that if an interrupt happens here in the middle of this, which then goes and tries to reschedule, that is bad because it's going to corrupt this state. So it's important to protect this critical section. And the way I'm doing this is by disabling interrupts. So yeah, if I'm not explaining it well, I'm sorry, we can talk about it more on Discord. Checkwab was asking, I think, Checkwab, you were asking about this part. Why is the interrupt different than the normal one? The difference is because the normal yield directly saves the execution context right at that moment. Yeah, so it's fine, no problem. Right, so there's, there's no problem. I think what I was just asking you is, do you also do this in your routines for doing mutexes and scheduling? Do you also disable interrupts? For me, that seems absolutely necessary. So, and so I just wanted to double check, since you have a more mature OS than I do, that you do something similar. Yeah, so back to over here. So yeah, like in general, the normal yield freezes in my case, it's handled by the timer interrupt. The yield function just triggers a timer interrupt. Interesting. Oh, it like, okay. Now I think I understand you. It really triggers a timer interrupt. I didn't even know you could really do that. Okay, we'll talk about it more offline maybe. But yeah, and so when task A is running, it calls the yield function, which like immediately like freezes its state such that it can be resumed. The interrupt handler is not trying to do that. It's not trying to freeze its own state, because we're not trying to resume the interrupt handler at a future point in execution. We're trying to resume task A at a future point in execution. And so we need a different API, and that's sort of what I want to explore. And so I took some notes about this. And so what this is going to look like, let's talk about this a little bit. So this is going to look like we're going to have task one. Again, I don't have interrupts yet, but I can simulate this code with exceptions. And so task one is running, trigger some int to simulate a timer interrupt. The int exception handler uses the special API to yield from interrupt. It doesn't freeze save the literally current running execution context, but rather uses the context that the CPU pushed on the stack. That's really the context we want to resume later. So we want to freeze basically this stuff, the registers that have been pushed here, and the RIP, and maybe RSP that were pushed in the interrupt frame. And then after we've done that, we want to select another task and then jump into it. But because we are doing so from an interrupt handler, we want to do an IRET back actually. And so I think okay, I also have this bug. I apparently was not saving the flags. So all right, feel free to join me. Another quick break. What's up, G? Jishnu. What's your educational background? I went to university to study computer engineering a while ago, and that's my educational background. I have a bachelor's degree in computer engineering. Okay, so I'm just gonna add a quick thing right now to our roadmap today. Fix the R flags bug. Actually, that's more important and urgent than anything else here. I have this R flags bug where I'm not saving the flag. Which is kind of a stupid thing to do. So, and it's kind of interesting that this has never come up. Let me just see where we're at. Okay. STI, no. STI. Okay. We got our code going. Including these big sleeps, which were kind of causing some problems, but so that's okay, that's going. So now, so I have a bug, like not really related to anything we've talked about so far. I just have a stupid bug in my code currently where at no point do I save the flags. I just don't do that. Just don't do that. What's a wall mark is how much for loops we need if we write it in an operating system. You need 10 million. I think is that how much? You need 10 million for loops for your OS. Yeah. So here's the bug. I'm never saving flags. And it would be interesting to see how we can... Our code's pretty stupid right now. And so that bug will never appear. So I'm just... What's something we could do? We could do... I don't know. What's something simpler? Just wild ones. We could just do... Okay, basically... 10. This is like pretty stupid. So here's what I'm thinking. We're never saving flags. So that's concretely going to cause a problem with like branching. The code here never really had problems because it didn't really branch around the yield. So I think the problem will actually manifest possibly now, because now we're actually branching around the yield. So let's just try this. All right. Okay, that did not do it. That still worked correctly. And I think that still worked. So I think what's happening is the R flags from like one task is like leaking into the second one. And because the for loop is the same, they remain in sync. So I think maybe a way to test this is let's make them not iterate for the same amount of time. Task 2 should run 20 times, and task 1 should only run 10 times. But here's the thing, our flags is getting leaked between the tasks. And I think the consequence of this is that this loop is not going to run fully. At some point, the R flags is going to say, okay, this comparison like is false or something, like we've already ran 10 times. It's going to stop execution of this function, but that flags is going to leak over into this task. However, this is going to keep updating the flags, I think. So I'm not even sure that I'm not quite sure. Okay. So that actually did it. That was the bug. Check it out. My understanding was not completely bulletproof there, but like that's the bug. R flags is not saved or restored correctly. It leaks between tasks. Task 2's loop stops early because of the flags from task 1 leaking into it. Something like that. So that's kind of interesting. The reason why I took the time to try to reproduce that is because now we can actually try to fix it and observe something. And the question is then, how do we fix this? So we need to save flags somewhere. Catch up on the chat. What if you write an OS with 0 for loops? I bet that's a good challenge. That sounds hard. I mean, you could use while loops maybe. Check while I'm fiddling around with long mode for the first time after the stream, since I only know 16-bit, 32-bit. Yeah, long mode is really interesting. Things are pretty different in long mode for the better, I think. It's really nice to have more virtual address space. The higher half and lower half concept is pretty interesting. Canonical addresses is an interesting concept. Segmentation is very different and simplified. Considering the fact how much code is written by AI, will you stick to manual labor now, no matter what? I'm going to stick to manual labor for the most important parts, where I really care. I'm not ruling out using AI for other parts of my OS that I care less about. For example, I care less about like the applications. I might vibe code applications for my OS because I'm less interested in writing those by hand. But I'm going to do the most important things. use AI to write debug messages. Yep. Sub shadow asking how I keep a single thing if I have 2 tasks. He jumps from one to another. Yeah, I just try to pick one thing. I mean, I wasn't even doing that very well this stream, but I just try to make one progress on just like one thing every time I work and not have too high expectations. And also to just get into a bit of a good flow. Okay, so the question is, where do we save e-flags? The obvious candidate is we just put another struct into this member. And the reason why I'm not directly doing that is because I'm not quite sure, I sort of forgot how this code interacts with the interrupt handling code. And the good news is that it doesn't, actually. The interrupt handling code has a separate structures for, interesting, has separate structures for storing stuff. So theoretically, I could actually use a GPR data inside the task register state. Yeah, actually to use GPR data. Okay, the main takeaway though is that, so the interrupt handling infrastructure has its own way of dealing with flags in the CPU data, which is the CPU pushed data, which is stored separately in this trap frame. But over here, I think this doesn't, actually, wait a sec, whoa, I need to be careful here because actually the struct offsets are important. Note the exact member order here is important. Offsets are hard coded in scheduler.s. So just to be really safe, I'm just going to put this at the very end. And then she says, write a print to dump all the struct members. I heard about this crazy thing from John Palmisk recently that there is, or no, where did I hear it from? I heard it from Jan Horn, maybe, Clang, debug print struct. There's like some special Clang. Yeah. This thing called built-in dump struct. Which will print out a struct. Like if you have a struct and you call this built-in, it prints out the struct, which is pretty cool. So that's why everyone should use Clang. That's why I'm glad I'm using Clang. I can take advantage of cool stuff like that. Yeah. So that's a win for Clang, in my opinion. All right, so we got our flags placed in a particular way that's not going to disturb the offsets of anything else. So now what we just need to do is update a couple of things. Maybe it's easier to start over here. Actually, wait a sec. How do you load? How does one save reload art flags? I don't even know. Can you just move into it or what? There's special instructions. Dang. Okay, it's giving me some like answer I don't want to see. So so unlike the other registers, you need to use some special instructions for saving and restoring R flags. And it requires the stack, which is funny and a little bit unfortunate. Oh, but you can use a PUSHFQ and then a POP. And that basically puts it into a register. So, okay, no one gives me the answer. I'm just going to try to think about how to do this. So, switch to task. Our goal is to take the R flags in the struct and load it into all the registers. We probably want to do this at towards the end, but not so close to all this, to like the push ret at the very end. So probably right here, I'm thinking. And what I want to do is I want to push. Yeah, I'm just going to do. Wait, yeah, I need to restore our flags stack, and so I'm trying to push. So RSP was at hex 80. So we got the hex 88, which is a cool number. We're going to push R flags onto the stack. And then we're going to, was it POPFQ? What's it saying? To restore, move something into racks from the save slot. Okay, push it, then pop. I think that's easy. I think that's pretty much what we're doing here. So we push the flags, and then we pop FQ. Okay, nice. Now let's do the other side of this. So we're talking over here, and what do we do? So now I need to push FQ, and then I need to pop it into a register. So we're using racks as the scratch register for a lot of things. And then this becomes an 88. Word. So I think that's looking pretty good. I think that is it. Let's run it. Let's run it up. What? Okay, that did not work. That's embarrassing. Ugh, okay. Okay, what's up, non-existent 1945 in the Twitch chat? Thanks for joining. Okay, what was my mistake? Okay, let me do some hygiene. So we got our little thing here. Whip. I mean, this probably just gets fixed up, I guess. So we're just fixing this up into the scheduler. What could I have done wrong? Okay, NSG with the sharp eyes. Be careful, since you're doing CLI just before the PUSHFQ. The interrupt flag is cleared, so make sure to enable that after restoring. That is interesting. That's a good call. Thank you for that tip. So, well, let me think about that for a second. So, make sure to enable that. Well, yeah. And so, wait. So the last thing I do before returning into a task is I re-enable interrupts. So do you think that should handle it? I think that should handle it. So, but yeah, it's important. Yeah, it's important to recognize that this R flags is going to have the disabled interrupt in it actually. So it's important anytime I restore a task from one of these structs, it's important to always STI. Yeah. So what's up, lonely guys? CS Bachelor. Just a little programming. Let me hit you with the resources page, which is a random website of links to things you might like. Non-existence doing great. Good to hear. I'm doing all right. Not awful. Insane piece of assembly coding today. Yes, sir. Okay. But are you seeing this? Something? What? What is going on? Task 2 should iterate 20 times. We're seeing things only run. I just want to make sure real quick that this is actually compiling and running, which has changed to 8. Okay. So yeah, now things run 8 times, so that's bad. It's bad that task 2. Oh, so what's going on? Yeah, what's going on here? So all right, time for another quick break. Feel free to join me for a little break. So what's up, Parth Sharma? I'm gonna see you again. It's been a while. All right. Non-existent fit an entire floppy communication protocol in the boot sector. What? Well, that guy's cracked for sure. So what's going on here? This is where our global task register state is we've put the R flags right after the RSP. RSP is known to be at offset 80. So I'm thinking that our flag should be at offset 88. Not that it really, I mean, save our flags into offset 88. Copy it into the register state. We get the task. We got the register state, and now gotta say I'm a little bit at a loss. I think the only thing to do now is like we could debug this. But to make this a little bit easier to debug, I'm just going to lower these numbers quite a bit. This is going to loop 2 times. It's going to loop 4 times. Yeah. Okay. What can I maybe use debug print? But really, I want to see R flags. Yeah, whatever. Let's just debug it. I'm gonna break on yield. Now that's annoying. Okay. Don't use templates, people. Okay, we've reached our first yield. And here's what it looks like. Task 1, colon yield, which puts us here. And we're just gonna do a little bit of stepping through it. So eyes over here. Actually, I guess both places. Same thing over here, really. So now let's talk R flags. That's fine, okay. So got a lot of flags. Those are R flags while task 1 is running. Hex 82. So that's what we're trying to restore later. So now I'm going to break on switch to task. Okay, but so we're saving. Well, let's just see. Let's just keep stepping through. So we know that our dang, sorry. Why is it? Why is it saying E flags? The upper 32 bits of R flags are reserved. Okay. Okay, so we observe that hex 82. So now let's just confirm this. Let's just keep stepping. Push FQ pop racks. What does racks look like? Okay, perfect. And this is the interesting part. Let's I slightly don't know what I'm doing. Oh my gosh. Okay. All right. So we got some nice zeros here. So now let's, as reminder, we're about to do this move racks into there. We got some nice zeros. Let's do a step instruction and check it out. We got some nice 82, a nice 82. So that's working. Sup, Steelau, do you have a GitHub of the project? I do not currently, but if you're interested in hearing more about the GitHub release, you can indicate your interest by joining my newsletter, which is where I'll talk about updates in that area. So that's how you can do that. Okay. So we just confirmed that this was being saved correctly. Now we can sort of finish this. Now we're over here. Why can I not? That's pretty annoying. 130. Is that 82? Good. So that's all good. We got our hex 82 there. And it's been copied appropriately. So now we can go how do I list breakpoints? So now we can break and continue over to here. But the thing is, that's just going to be the code where we switch into task 2. So we're now switching into task 2. We don't really care about that. I'm going to continue one more time, and we should be back. We should be in the call where task 2 is yielding now. So now task 2 is yielding itself. And it's gonna do that. We can step through that just to see what. Racks is also 82, so nothing crazy. We're gonna continue one more time. So now here's sort of an interesting moment where we're going to restore flags. Okay, I did not. Okay. So now we're just gonna try to here. Check it out. So let's just take a moment to examine okay. Why is that not working? Man, I'm a noob. How? I need to. I just want to. Oh my gosh. Okay. Make sure you're using the $sign. So perfect. We got the hex 82 there. Just like we wanted. We're going to push it. Let's check our stack. A nice 82 on the stack. Flags is 86. And we're going to POPFQ, right? That's the instruction. So we're going to step instruction. The POPFQ just ran. Okay, our flags are nicely set. And we're ready to go. We're ready to hop back into the task. So we popped right back. We popped out. We're now returning from the yield call. And we got the 282 because the interact flag is now enabled. So that's expected. That's the only other thing that's enabled. So it's looking good. It's looking good. So now what's next? So as far as I can see, we're back. We've totally resumed task 1 correctly with the flags. So I'm just going to continue. So now we're back, and task 1 is preserving itself again. So we'll just step through. It's still 82. So that's good. Come in here. We're gonna so now we're switching back to task 2. And I think we should yeah, task 2 still had an 82. So we can look at our stack, 82, good. So now we're back over here. Now task 2 switching back to task 1. We should also still the 82. So we're just really confirming this. Okay, coming back over here. And now we are at I lost track of things a little bit. Resuming some task. Oh my gosh. The key point is just that like I sort of forgot exactly what like so far it's just been 82s all across the board. So still 82, good. So And at some point, so now we're back in task 1. Okay. So task 1 is pretty much done. We've yielded twice in task 1 now. So I don't think we should really be continuing execution more. So let's, yeah, task 1 is done. Oh, that's why. That's why, okay. That's why, okay. And that's why we see the freeze, because we never yield. Okay. This cooperative multitasking takes a little bit of getting used to. I need to have a yield here just to ensure that task 2 can ever get the CPU again. That's why. Otherwise, we just sort of spin forever. So that's the deal. Okay. Let's try that one more time. So here's what I'm going to do. So this should work now. We should see 2 and 4. We're just going to go back out here. Okay, that didn't work because, okay, what I need to do is wrap. It's kind of funny. After they're done, they're just going to schedule each other forever. And that is just going to make sure, right? The reason we see this thing made a little bit, this thing made one more loop of progress because it looped, but then it hit the schedule again, which resumed back over here and just hit the while loop. And so it's sort of stupid, but we just need to make sure these things are just scheduling all the time. Just to make sure things get opportunities to run. And so this is going to, like, during this, the excess iterations for this task 2, it's going to be calling yield, which is going to be resuming here, which just yields again. So, our moment of truth, we should be seeing it work right now. Task 1 runs twice, task 2 runs 10 times. That's working. Some question in the chat. Sri Balasu Pramanian, what is the name of your OS? There's no name for the moment. And what's up, Hello Code? Nice to see you. What's up, the BioKids 5? How do you even get into this stuff? There's different ways to do this, but I think one great way to do it is through computer security and learning to write exploits for software. Non-existent asks, how long have you been working on this? It sort of depends on when you start counting, but about 2 years, basically, starting from the total beginnings. Okay, let's break it again. Let's break the code. I'm gonna comment out a couple things. Just, it's always important, I think, to make sure you see the broken code, the broken state. This is interesting because it even still seems to work. Even when I've commented things out, I think the problem is that let's flip it. The problem is that task 1 exits earlier. Let's flip it around. This thing's gonna run 10 times. This thing's gonna run twice. And it still seems to be working. What? I think it's still working because I think the threads are clobbering flags by executing the comparison instructions. So I don't know if they're really relying on state. I'm going to jump to the AI. Please suggest task 1 and task 2 changes to cause some observable bug if our flags is not saved restored correctly. I'm just gonna defer that thing to the AI. Okay, it's setting something with the direction flag. Yes, do the DF thing. Okay. Okay, so in this case, it's actually done like asymmetric operations. And let's just run this. I think this should probably fail. Yes. Assertion failed. Okay. Now I'm gonna re-enable my fixes. Run it again, and it should. It's not failing, so there we go. So, okay, that took kind of a while, but the R flags are fixed. We're now saving and restoring R flags correctly. All right, and with that said, I'm gonna slowly bring the stream to a close. Thank you very much for watching. If you're tuned in right now, the 18 people, please subscribe to my channel if you enjoy this content. I would really appreciate that. And if you want to chat more, we can do that in the Discord. Feel free to join the Discord. I'm going to sign off, and I hope you all have a great week. I'll see you next time. Peace.